The voter registrations for a certain city show that 40% of its population is registered as Democrat, 45% as Republican, and 15% as Independent. A poll of 100 citizens showed that 36 planned to vote for the Democratic candidate, 41 planned to vote for the Republican candidate, and 23 planned to vote for the Independent candidate. Can it be concluded at the 0.05 level of significance that this particular election will vary from the registration proportions? So, what would be expected if the citizens vote according to the registration proportions is that the proportion of those who would vote Democrat would be 0.4, 40%. The proportion of those who would vote for the Republican candidate would be 0.45. And the proportion of those who vote for the Independent candidate would be 0.15. This is what is expected. These are the proportions. If we go by the registration proportions, this is what should be seen in the election. This will be our null hypothesis. The question is, can this be contradicted by the data? Let's write that down. Can these proportions be contradicted by the data? Now, in a case like this, where we are testing about more than two proportions in what is called a goodness of fit test, where we are testing how well the observed values fit the expected proportions, we're going to use what's called a chi-square test. And we would use the Greek abbreviation here for chi-square. Now our alternative hypothesis, and if we think about this for a second, if any one of these changed, then at least one of the others would have to change in order for the sum to still be 100%. So our alternative hypothesis will be that at least one of these proportions varies from those in the null hypothesis. Again, if we think about that, if just one of these is different, then this distribution of proportions is not as what we have stated here in the null hypothesis. Now the chi-square curve is a curve that has a long tail to the right, and this will always be a right tail test. And we can see why that would be by looking at the chi-square test value and its formula. Here's what the formula looks like. We're going to add up, so there's a sum symbol. We're going to take observed values, and we're going to subtract from them the expected values. And then we're going to square that and then divide it by the expected value. So what's going to happen then is we're going to, for each of the observed values, we will subtract its correlated expected value, square that value, so it's going to get positive and a little bigger, and then we'll divide that by the expected value. Now, this is always going to be positive then. This value will always be positive because we're going to take a difference and square it, which will make it positive, and then divide that by a positive number. Now, what happens is if the difference between the expected and the observed values is large enough, then this numerator gets large. And then when we add up a bunch of terms that are getting larger and larger, we accumulate some value. So the question is, do we accumulate enough value to overcome a chi-square critical value? Now, the chi-square critical value will depend on some degrees of freedom. And in this case, in what's called a goodness of fit test, for a goodness of fit test, the number of degrees of freedom will be one less than the number of categories. Okay, well, we have three categories: Democrat, Republican, Independent. So we have 3 minus 1, or 2 degrees of freedom. Now we can find this critical value by going to Stat, Calculators, chi-square. Degrees of freedom is 2. If we're going to do a alpha level of 0.05, then we're going to put 0.95 here and leave this at less than. So we're accumulating 95% of the distribution. And you can see that's what we have here. We have 95% of the distribution, and then 0.05 out in this tail. And that critical value will be 5.991 if we round to 3 decimal places. We could also do that by making this 0.05 and making this greater than. And we get the same thing. We just have the area, the red part, listed up here rather than down here because of the change in the direction sign. But either way, we have 5.991 as our critical value. So our chi-square critical value is 5.991. Now, our test value we're going to get by doing, okay, let's see, we've got some expected values and some observed values. So we have our observed value here in the first case is 36 minus the expected value, 40. And then we're going to divide that by the expected value, 40, and we square what's in the top. Plus, and now we'll do that again for the next category here. So the observed is 41 minus the expected 45. That'll be squared, and then we'll divide that by the expected 45. And then we have, again, the observed 23 minus 15 squared divided by 15. And that value comes out to 5.022 if we round to 3 decimal places. Now we note that this is not greater than 5.991, and we decided that if this value became large by the exaggerated difference between the observed and expected values, then we would believe that the actual proportions are different from what we see in the null hypothesis. So in this case then, we did not land up here in the rejection region, so we do not reject the null hypothesis. Now we can use the TI-84 calculator to find this value. We'll push Stat, and then we'll go over to Tests, and we'll go to Goodness of Fit Test, which is chi-square goodness of fit test, that's D, and then we'll hit Enter. Now it wants to know which list do we have the observed values in and which list do we have the expected values in. So we're going to need to go type those values in. So we'll go to Stat, Edit, and we'll clear list 1. So we'll do that by highlighting the list name and hit Clear and Enter. And now we've cleared that list, and we're going to want to put the observed values in that list. So that'll be 36, 41, and 23. Then we'll put the expected values in list 2. So that will be 40, 45, and 15. Now we'll go to Stat, Tests, Goodness of Fit Test, that's D. The observed values are in list 1. The expected values are list 2. Our degrees of freedom was 2. Since there were 3 categories, 3 minus 1 is 2. And then we're going to come down here and hit calculate. And we see we got these same numbers. We've got 5.022 for our chi-square value. Now let's also note our p-value, 0.0812. So our p-value is 0.0812. And this time, our p-value is greater than alpha. Alpha was 0.05. So again, this leads us to the same conclusion. Do not reject the null hypothesis. So as usual, we can use our critical value and our test value, pair those up and make our decision, or use the p-value and alpha and pair those up and make our decision.